All right, ladies and gentlemen, today's class recording has started. So, we're going to start off today, we're going to talk a little bit about magnets and magnetic fields. I'm assuming that all of you have experienced a magnet before, yes? Right? You understand what a magnet is, right? What it does, and stuff like that. So, you are not the first person that has figured out what a magnet is. Magnetic properties have been around for a long time. Way, way, way back in antiquity, if you want to use a big fancy word like that, right? We knew about magnets. We didn't know they were magnets. We didn't know how they worked, but we did know that there were certain kind of minerals that would behave differently than other minerals. For example, something called lodestone. Lodestone has a bunch of iron oxide in it. Iron is, now we know, a magnetic material. So this lodestone, it was a rock, but if you kind of set it in a way that it could twist and turn, putting a piece of lodestone on the ground really doesn't do a whole lot. If you put lodestone, a piece of lodestone sitting on like a piece of paper floating in water, or like now if we had like a paper plate and you put it in water, it will align itself up in a certain direction all the time. And so that's basically our first compass. These stones that we just get out of the ground do this naturally. We didn't know why, we didn't know how, but we knew that they did, right? So that then turns into, right, fun things that you can do as a baby, like put little letters on the refrigerator and start cat or dog or mom or whatever, right? And most of you have experienced that before and you've kind of seen those kind of things before, right? But we've also learned that there's two things that magnets can do. Some magnets will attract each other, right? And some magnets will repel each other, just like electric charges. And that's not a coincidence. There's a reason why that happens, right? Because electric charge and magnetism are closely related to one another, which we will get into more next, or at the end of this week and beginning of next week, but there is a relationship there, right? So, let's talk about magnets, okay? First, magnets have two sides, right? And we separate them by how? How do we distinguish between the two sides of a magnet? Red and blue, or we call them, we usually don't call them positive and negative. What do we label one or so? Here, Frank. Hold on. We call them poles, right? And we label the poles as what? North and south. Right? Let me go over here. And we label our magnets north and south because, right, one end of this magnet is always attracted to one part of the earth, and the other part of this magnet is attracted to the other part of the earth, right? So we label the north pole of the magnet the one that points towards the North Pole. We label the south pole of the magnet the one that points towards the south pole, right? So this north pole on this magnet is the quote-unquote north-seeking pole. It's the one that points north, which in this room would be that one, all right? Well, one, because I know my directions, but two, because you may have noticed this magnet that's been hanging up here for the past, like, 5 months or whatever it is, and it always points that way because that's north, right? And the lake is that way, right? But here, right here, if you want, I'll spin it, and then by the end of the period, you'll see that it sets itself up that way. Yeah, so north is that way in this room because, yes, I know my directions, the lake is that way. All right, but then, right, the other side is labeled as the south pole, right? It points towards this Earth's south geographic pole, right? So it's the south-seeking pole, which hopefully you filled in because it's exactly the same as the north part. I just want to verify that it actually happens in the period it's playing the way that it's supposed to. Actually, I will tell you that there's a twist to that magnet. So, not, the figure is a twist, not like that. It's twisting right now. There's some irony, if you want to use some literary terms, because you guys have to take the English classes, you know. So, all right, good there? One thing or one way that magnets are different than electric charge. There's a lot of ways that they're similar, but there's one big way that they're different. Okay? Magnets always have two poles. If we break a magnet in half, we don't end up with a North Pole magnet and a South Pole magnet. We end up with two smaller magnets that have a North and a South Pole. Okay? Breaking a magnet in half produces two new poles. So in this case, it produces a new South Pole and a new North Pole, oriented in the same direction that the original North and the original South of the original magnet were oriented. We have never found what we refer to as a magnetic monopole. Right? Because we know English, can we figure out what that means? One pole, right? We can have a singular positive charge, right? What subatomic particle contains a singular positive charge? Proton. We can have a proton with no electron. We can have an electron with no proton. You cannot have a North Pole of a magnet without a South Pole of a magnet. Even if you break it in half, basically two new poles get created. If we took these two magnets, these two smaller ones here, and broke them in half individually, we'd have four magnets now, each with a North and a South Pole. We can't isolate the North Pole from the South Pole, and we'll talk about why that is here in a little bit. Okay? Good there? So, magnetic force, right? Magnetic force is the force that magnets exert on each other. And what kind of force magnets exert on each other, check the outline here, the lab is later. But. So, the kind of force that magnets exert on each other depends on the poles, right? And I think most of you know what happens when opposite poles come near each other. If we have a North and a South Pole, they attract each other. If we have a North and a North Pole, they repel each other. And you can see that in this picture here. Okay? But
you just said that.
And now everybody knows it. But one thing that we have to address, right? Do these magnets have to be touching each other to apply forces to each other? No, right? And that means what has to surround each magnet? A field, right? Remember, electric charges can exert other forces on other charges because they have a field that surrounds them. Magnets can exert magnetic force on each other even though they're not touching because they are surrounded by a magnetic field. So let's talk about the magnetic field, right? Hopefully this picture, even though we didn't look at a magnetic field, you can kind of figure it out, right? What did we say the arrows represent? What do we call those arrows? They're field lines, and they represent the field, right? So, a magnetic field is an area that surrounds a magnet where it can influence the behavior of other magnetic things. The field still exists even if there aren't other magnetic things around it, just they don't do anything. So a magnetic field is an area that surrounds a magnet where it can apply forces to other magnetic things. So the field lines, these arrows, represent, or they flow from the North Pole of a magnet to the South Pole of a magnet. And you can see that those arrows in that field that's on your outline is the same one as in the picture right there, right? Notice the arrows flow from north to south. And that's how magnetic fields flow. You have a space before magnetic field lines, points, right? Oh, sorry. Fill in the blank, right? I mean, so how do magnetic field lines point? Away from north poles and towards south poles, right? you might actually have to like pay attention instead of trying to play that game. Yeah, I'm sure. I'm sure. You realize that you're breaking the rules of the air test by talking about it on recording. Just, there's evidence. So. All right, good with the magnetic field. All right. So, all these pictures are not what I wanted here. So let's get rid of these pictures right here. All right, and let's go here. So here is sort of a classic way that we represent magnetic fields. So these pictures are showing small little pieces of iron. We call them iron filings. They're like iron dust, right? And showing you how they line themselves up around a magnet. They show the field. The one in the top left, right, you can see that there are lines that go from one pole to the other pole. Now, obviously the arrows don't really tell you, right? You can't see the arrows, but you can see that the field flows from one pole to the other pole. Here, in the top right, what are we seeing in between those two north poles? Nothing, right? What happens in that case? What happens to the field in that case? The quick explanation is what happens to the field? It's gone, right? Not because there is no field, but what's happening to the two fields there? What are they doing each other? They're basically canceling each other out, right? So we see that empty space between the two north poles. But when we go a north and a south, right, what are you seeing between the north and the south pole? A lot of little iron filings, right? The field is very strong in between a north and a south pole because, like we said, the arrows flow from north to south. So a real strong field between the north and the south pole, okay? On the right, bottom right, we have a horseshoe magnet. A horseshoe magnet is just a bar magnet that gets bent into a horseshoe shape, right? So there's a field that's surrounded. It goes from the north pole to the south pole, but it looks a little bit different just because of the way that the magnet is shaped, all right? Good there? All right. What we have figured out over time is that the Earth has its own magnetic field. At the time, back in antiquity, right, we would use that big word right at the beginning, when we talked about lodestone, nobody knew about magnetic fields and how they work and stuff like that, but now it makes sense. If we have a magnet that orients itself to point towards the North Pole, it's in a field. That field is the field caused by the Earth. So, you can see here, right, this picture of the Earth's magnetic field. There's field lines that flow. Hey, Amanda, you can grab that, the outline that we're working on. You can see that the field lines flow from one part of the Earth to the other part of the Earth, right? If you look at the picture, which way do the field lines go? They start at the South Pole, and they flow to the North Pole. All right? Keep in mind, okay, now, make sure we keep this straight as we go through this, okay? The Earth produces a magnetic field that resembles a giant bar magnet. Obviously, it's in 3 dimensions. The field that surrounds this bar magnet is in 3 dimensions, too. We always think of it as in 2 dimensions, just drawing these arrows, but there are some arrows that come out on the z-axis. If we go, does that make sense? Right, if I put it as z-axis, right? So, we call, sorry, break this down, then we'll discuss. Break this down. Because the north-seeking pole of the magnet, or the north pole of the magnet, always points towards the north geographic pole. The north geographic pole is actually the south magnetic pole. Do we have that written down? Okay, so let's make sure let's make sure that it makes sense, right? Okay. So this magnet, North Pole, South Pole, right? We call this the North Pole of the magnet because it points which way? Points towards the North Pole. But if the North Pole of this magnet is attracted to the North Pole where Santa Claus lives, right? What does that mean about the pole of the magnet that's underneath Santa Claus's house? It's got to be the South Pole because North and South are attracted to one another. So when we talk about the poles of the Earth, we have to talk about and make sure we distinguish between the North geographic pole, which is like where it appears on the globe, versus the North magnetic pole, which is how magnets act. Okay? This side of the magnet, labeled S, points towards the south geographic pole. What that means, that's the north magnetic pole. Okay? And you can see from the picture, it might not be clear in your copy, but you can see in the picture here, right? If we draw Earth to resemble a big bar magnet, right? Where is the North Pole of the bar magnet? At the South geographic pole. And the South Pole of the bar magnet is at the North geographic pole. Right? So let's make sure that we keep those things straight. Geographic pole versus magnetic pole. Here's a fun thing. As we look over time, what we see is that the poles of the magnet that is planet Earth keep flipping. That over time, currently, the North geographic pole is the South magnetic pole. The South geographic pole is the North magnetic pole. So this magnet lines up the way that we line it up, or that it lines itself up. But give it a couple thousand years, 10,000 years, 100,000 years or so, and the Earth's magnetic field will flip. And the North geographic pole will also be the North magnetic pole. And the South geographic pole will also be the South magnetic pole. So what would happen to this magnet? Go the other way. So does that really change our lives in any way, shape, or form? No. Not really. All right.
The compasses get screwed up.
The only thing that the only thing that is different about a compass is usually on a compass, when you look at a compass, the little pointer thing has two sides. It has a red side and a white side. And the red side points towards the North Pole. Now the red side would point towards the South Pole. Would the compass still work? Technically, yeah. It would just be backwards, right? You know, like so. Or now you'd have to follow the white side of the compass instead of the red side of the compass, or whatever. Right? So, how do we know that? Well, remember at the very, very beginning we talked about lodestone. Lodestone is just a rock. Okay? And what we find is that if we look at rocks on the ocean floor, are we familiar with plate tectonics and how that works? Right. Mid-ocean ridge, the magma comes up, all that good stuff, right? When we look at those rocks, what we find on the ocean floor is that if we have magnetic rocks, things like lodestone, in the red sections, the North Pole of the lodestone points towards the North geographic pole, like we have now. But there are certain sections of the ocean floor, like these lighter ones, where the north pole of the lodestone points towards the south geographic pole. So it just keeps flipping back and forth, back and forth, back and forth. Why? Good question. All right. So before we answer that question, Sammy, let's talk about this question. Why are things magnetic to begin with? Okay. We've mentioned that there is a connection between magnetism and electricity. Okay? Moving charges, and this will be important when we get into our stuff later on this week, or later on this week and then really next week. Moving charges cause magnetic fields, right? In the last unit, we talked about the moving charges. What do we call moving charges, or in the beginning part of this unit? A bunch of charges moving through a conductor. What do we call that? That's current, right? What we will see, let's start this on Friday, is that current actually causes a magnetic field, right? That's when we have a bunch of charges moving. But even one moving charge will cause a magnetic field. What's on the outside of an atom? Electrons. What are electrons doing? They whiz around the nucleus, right? That's a moving charge. So every atom itself is inherently magnetic. But magnets affect other magnets around them. Okay? So all these little atoms with their moving parts are magnetic by themselves. The atoms surrounding the atoms, the other atoms, right, they all sort of line themselves up because, right, opposites attract, like poles repel, blah, 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 blah. So we end up with these little sections in every material called a magnetic domain. And this picture, these two pictures, which you have at the bottom of your outline, right, show magnetic domains. So see in picture A, right, there's a bunch of these little sections that are broken up into chunks, blah, 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 and each of them has an arrow in it. And that arrow represents the magnetic field, right? It points away from north and towards south. Okay? On the left, in picture A, what are you seeing about the direction of all those arrows? It's all real random, right? So even though this little part of, let's say that this picture represents my magic pen, okay? Within my magic pen, there are individual parts that are magnetic. We call those domains. But the way that they're all arranged in picture A, they're all canceling each other out. So is my magic pen magnetic? No. But if you look at picture B, what are you seeing about those domains? Most of them, maybe not all of them, but most of them are all going the same direction. So now we have all of them kind of pulling in the same way. And their fields all pull the same way. What does that mean about B? It's magnetic. Okay? Because the fields are all lining up together. In most materials, the fields created in each domain are all at random angles and essentially cancel each other out. Okay? Now, in magnetic things, the fields are all lined up. The domains are all lined up basically in the same direction. So they're magnetic. Here's the trick though. Paperclip, right? A paperclip is not magnetic, right? Unless you bring it by another magnet. Okay? So, what happens in something like a paperclip is that on its own, all the domains are kind of random like this. So it's not magnetic. But remember, outside fields like this can affect the fields inside of the paperclip. And it lines them all up. And so the paperclip becomes magnetic when it's around another magnet. this magnet is permanently like picture B. The paper clip, when there's no other magnets around, looks like picture A. But when another magnet comes around, now the domains line up and it looks like picture B. But if we take the other magnet away, it goes back to being A, right? And so we refer to that, right, that's what happens in a paper clip. When a strong magnetic field from another magnet comes close, the fields in each of those domains line up. The combined effect causes something to become magnetic that maybe isn't magnetic normally, right? This magnet has no effect on this dry erase marker under any circumstances, right? These fields aren't able to be manipulated that way. But the fields in some things, like paperclip, can be under certain circumstances. The domains inside of this magnet are always lined up. That's why it's permanently magnetic, quote unquote. Okay. Good there? All right. And I think that is the end of the outline. All right. So let's take a little break. And then let me go check on what's going on in the library. And if the library is still being used, I'll try to stop this recording. So.
Should we just use the Chromebook?
Chromebooks are being used.
All of them?